Hi, welcome to the second part of the final probabilistic programming session. Today we'll be doing dynamic models, specifically a linear Gaussian dynamical system. So the problem is as follows. We're considering alpine railways. So these are a set of carts that are on rails, on tracks that follow a mountain upward. And so they bring hikers and skiers up into the mountains, up into the Alps. They're not a cable cart, and they're not a train, like a diesel train or electric train. They're just carts on a track, so they move at a constant velocity. The Swiss Federal Railway Company contacts you and asks you for your help. So they operate a series of these mountain railways, and they are setting up a new fallback security system. And they want to track the trains, the cart's position through cameras and remote sensors. So they want you to design a system to keep track of the cart's position. So a cart or train going uphill updates its position according to a very simple equation. So the new position is the old position plus the velocity times the length of the time step plus some noise. And this noise represents the cart randomly slipping or jolting back up. We observe the train then through a remote sensor, which produces noisy observations of the true position. So we have a data set. It's shown here below. The red line is the true position of the cart over time. So it's laid on a series of tracks going up a mountain. So that's what explains this this dip, and then the black dots are the observations of the true position. So let's go to the model specification part. So we define noisy observations y to be one-dimensional real-valued numbers. So those are observations of the position of the cart. And then we have latent state x, time k, which are two-dimensional real-valued numbers. So these are the true position and the true velocity of the cart. So as I mentioned, observations are generated through a Gaussian likelihood centered on an emission matrix C times the current state x of k, perturbed by some measurement noise with covariance matrix R. So if we have the true position and the true velocity, this emission matrix C, it masks out the velocity. So we take the true position and then add some noise. That generates the observation. This is a dynamical system, so not only do we have observations, but also the states evolve over time. So there's a temporal dependency between states, which is captured in a state transition. These state transitions follow a Gaussian distribution centered on a transition matrix A times the previous state, and that's then also perturbed by process noise with covariance matrix Q. So just to be clear, in equation form, these are the P of the current state. P of the current state given the previous state is a Gaussian centered on transition matrix times the previous state with covariance matrix Q, and then the probability of the current observation given the current state is Gaussian centered on the emission matrix times the current state with measurement noise with covariance matrix R. So we also have this entire thing depends on having a prior for the previous state. So what we're doing here is a filtering setup. So we're doing recursive estimation. You start with an initial prior, so that's P of x0, and you define the parameters for those yourself. So you say m0 and v0, and then you would apply at every time step. You would take that prior, apply the state transition and the observation likelihood, and then you'll be able to estimate the parameters of the current state x of 1, and then time moves forward, and the parameters of the estimate of the state x1 become the parameters for the prior x1, and then you apply the state transition x2 given x1, and then the observation x2, and then the parameters of x2 become the prior in the next iteration, and so forth. So this is actually a very efficient inference procedure. So and you can see that in the conciseness of the graph that we will specify. We have this initial state prior xk minus 1, and we say that its parameters are going to be observed. So we'll just update those every time step in the actual inference procedure, which we'll see in a minute. Then we have the state transition x of k, which is Gaussian distributed with a mean, which is transition matrix times the previous state, and then a variance with this process noise q. And then we have an observation likelihood y of k, which is Gaussian distributed with a mean. So because the emission matrix here is actually a vector, it's just 1, 0, because it masks the states. It collapses the states into a lower dimensional object. This becomes a dot product, so the dot between the emission matrix C and then the current state x of k. And then we'll have this measurement noise covariance matrix R in there. And so the current observation is observed. So that produces the following graph. It looks a bit longer than you might think, but this thing is so again we have recursive estimation procedure. So we'll just take a subgraph and then repeat that over time. So let's start at the bottom. We take the previous estimates of this. The estimates of the previous state. So the parameters of that of the previous state estimate. We plug those in here. That produces the prior Gaussian xk minus 1. Then we multiply that with the transition matrix, which is here, this clamp 1. That produces the temporary variable 1. This is Gaussian with clamped covariance matrix q, which is then overlaid, which produces the current state x of k. That current state x of k is then taken with a dot product through with the emission matrix C to produce the temporary variable 2, which is then added to the variable 2 is measurement noise covariance matrix R to produce the current observation y of k, which is observed. So now we'll construct the algorithm. So you might notice that this is not a variational Bayesian procedure. We don't actually need variational Bayes in this case. When we're just estimating states, that's the only unknown. We'll just use Gaussians. We have a Gaussian state prior, we have a Gaussian state transition, and we have a Gaussian observation likelihood. So all of the integrals will be analytical. We'll know all of the results analytically. And so we'll be able to do exact Bayesian inference for the state estimates. Now, as soon as this becomes a little bit more complicated, you won't be able to do exact Bayesian inference. So if you don't know the covariance matrix Q or R precisely, or if you don't know the transition matrix or the emission matrix C precisely, then you'll need to estimate those simultaneously. And you can do that, but we'll have to resort to approximate Bayesian inference, so variational Bayes. We'll have to put a prior on these unknown variables. So for the noises or the noise covariance matrices, we'll have to put Wishart distributions. And for these, depending on what kind of coefficients they are, what kind of structures in that matrix, well, you might use Gaussians, you might use something else. But if you have more unknowns, you'll have to be able to estimate multiple unknowns at the same time, and we'll fall back into a variational Bayesian procedure where you just do updates for two recognition factors, two or more recognition factors. Right, so well, it actually makes everything quite easy. We just say we want a message passing algorithm for the current state x of k. If we then execute this, we will have to initialize the marginals dictionary and we only need the current state x of k, and so we can do that with say that the marginal is supposed to be a Gaussian mean variance. I am going to have a look at the messages that are being passed later on, so I'm initializing a message array here. And I would like to keep track of the parameter estimates for the states over time. So I'm initializing two matrices that are going to be populated as we move through the dataset, as we move over time. So as I said before, so we're iterating over time, starting at case 1. So due to the nature of indexing into a vector, so we can't index into k minus 1 into 0 here, so we'll start with 1, and we're going to update the next parameter estimate. So at time step 1, you have to read this as at time step 1 we are observing the current observation, and then we are taking in the kth parameter estimates, which represent the parameter estimates of the prior state. And so how you initialize these, then this is also how you initialize the parameters of the initial state prior, so px0. So so these are of course placeholders, these mx and vx structures, but then the very first entry represents the parameters of px0. So because I started this with zeros and then an identity matrix, for this I'm actually taking p of x0 to be a mean of zeros, and the covariance matrix is an identity matrix. So that'll be our first state prior, and then we'll do an update. So we're going to use the data to update the marginals, and I'm actually also going to populate this message array. So now we have an estimate for x1, we have a marginal for x1, and then we can take the mean and covariance from that marginal. We'll store that at the location k plus 1 in the in the vectors mx and vx, and we'll just continue through the entire time series like this. It's actually quite fast, this procedure. You can imagine why it's very efficient. It's only a few computations per time step. So if you visualize the inference results, that looks like this. The blue line is the mean estimate, so those are the mx's over time, and you can see that it actually follows the true position quite nicely. What we'd like to see with this ribbon surrounding the mean estimate, so that's the standard deviation, so of the 1,1 entry of this covariance matrix, we'd like to see that this ribbon encloses the red line, the true state, which it mostly does, except for this part of the bump. We're going to inspect some messages. So we can do that by, before we get to that, let me just first show where we need to look for, which messages we have to find. So the message array will be populated again and again every time step. So the fact that we ran this up until capital T means that the message array is currently populated with the messages to compute the final x of k. So if you look at the source code, you can just do that by print line source code. You'll see the generated step function. You can see, so it's a bit hard to parse what's going on here, but the only thing I want you to see here is that the marginal, the current marginal x of k is the product between two messages 3 and 5. So we're going to visualize those two messages 3 and 5. So message 3 actually comes from the state transition. So the state transition sends a message towards the current state x of k, and the likelihood also sends a message upward to the current state. And you can see that here. That's the red line is the message from the state transition, and then the blue line is a message from the observation likelihood. And then you take that product, and that forms the marginal for the current state estimate. The green Gaussian. Yeah, so and then this is essentially what happens at every time step. So there's a Gaussian message coming from the past as a prior from the state transition, and then there's a Gaussian message coming from the likelihood that updates the marginal, essentially the posterior for the current estimate, for the current state, and that posterior becomes the prior in the next time step, and that's how we move on. It's a very efficient procedure. So now we come to the final try for yourself block. I want you to rerun the inference procedure, but then stop at an earlier time step. For example, k is 2. I would like you to visualize the messages again and then see how this balance between the state prediction and the observation likelihood differs. So if you change this, so say that you for some reason would like the initial state p of x0 to start at 10 times once, then you'll, or maybe the initial covariance matrix is quite wide, so maybe you're uncertain about the initial state. You'll see that the state prediction will be quite far off, and also will be quite wide, and you'll see that the state estimate will mostly be dominated by the observation likelihood. And then as you go through the time step, the initial prior will be washed out. Right, so that's the end of this probabilistic programming session, and then the end of the entire probabilistic programming sub-part of the course. Yeah, so I hope you had fun. There's lots of ways to expand upon each problem set that we treat, so especially last ones, regression, classification, latent variable models, and dynamic models. There's lots of ways in which you could expand these models, make them richer, makes them more suited to very specific problems. And so I hope that with these 4 probabilistic programming sessions that I've given you the basic tools to get started with probabilistic programming, and that you'll give this a chance in your graduation project and later on as you dive deeper into your engineering career. Yeah, again, I hope you had fun.